For the purposes of this course, we'll just need to have a basic understanding of what hypothesis testing is and how we can conduct and interpret hypothesis tests using SAS. And it seems natural to begin a discussion of hypothesis testing with a discussion of what a statistical hypothesis is. Every statistical hypothesis test has a null hypothesis, denoted with an H sub 0, and an alternative hypothesis, denoted with an H sub A. Think of the null hypothesis as the default, an explanation for the way things are assumed to be that we're trying to discredit. For example, that the Earth is flat. The alternative hypothesis is the way we think things really are. For example, the Earth is not flat. Note, however, that there are important differences between the Earth is flat hypothesis I just used as an example and the statistical hypotheses we typically test in public health. Mainly, we can take a bunch of satellites and measure the entire Earth to reject or fail to reject our null hypothesis that the Earth is flat, which we of course reject in this circumstance. In public health, this is tantamount to having complete data on our entire population, which is almost never the case. Instead, we take measurements on a small subset of the population and try to figure out how good of an approximation that measure is for the entire population. That's really more like rejecting the world is flat hypothesis based on a single picture or measurement of 1 square mile of the Earth. And because this video is about testing for differences in means, we don't just want to know how much our sample is like the population we drew it from. We really want to know whether one population is different from another population, based only on a sample from each population. Practically, what we want is a measure of certainty that the conclusions we draw from our samples are the same conclusions we would have drawn had we measured every single person in the population. When the measure we're concerned about is a mean value, like mean height, and we're only comparing the mean value from 2 samples, we can get this measure of certainty using a t-test. In this situation, our null hypothesis is that the means are the same in both populations. Our alternative hypothesis, the way we think things really are, is that the means of the populations are different. Before going any further, let's take a look at how to calculate these measures using SAS. Here we're using the t-test procedure to test for a difference between 2 means. Although the t-test can be used in other ways, in my experience this is the most common use in public health. You can see that the syntax is identical to proc means, except that we type the keyword t-test instead of the keyword means. And by default, SAS gives us a whole bunch of results. The top table is almost identical to the results generated by proc means, except that there's now a 4th row that gives you the estimated difference between the mean height of males and the mean height of females, and the standard deviation and standard error of that estimate. The second table is basically the same information, except the 95% confidence interval for the means and standard deviations are given. The third and fourth table is what we're really interested in for this next discussion. Recall that the null hypothesis for a 2 independent samples t-test is that the means of the 2 populations are equal. In the present example, that the true mean height of males and females is the same, and that our goal is a measure of certainty that the conclusions we draw from our samples are the same conclusions we would have drawn had we measured every single person in the population. In order for the results we get from our proc t-test to allow us to accurately do that, there are some assumptions that have to be met. First, the observations in your sample must be statistically independent of each other. In other words, one observation doesn't affect another observation. For example, your height isn't affected by the height of anyone else in the class. However, this assumption would be violated when your data is person period data that contains multiple observations for the same person. For example, my height 2 years ago affects my height today. Second, the distribution of values in the populations you're comparing are normal. We've already learned a couple ways to graphically check for normal distributions. Proc t-test produces 2 of these graphs by default. Fortunately, even when the data is not perfectly normally distributed, the t-test tends to lead us to accurate conclusions, particularly when the sample is large, say 50 or more. And third, the variances, or spread of values around the mean value, should be equal in the populations you're comparing. You can verify this assumption by comparing the variance of your samples. If your sample variances aren't very different, then there's a good chance the variances in the population your samples are drawn from are not very different either. We can and should test all of these assumptions in SAS before drawing conclusions from our t-test. And that brings us back to where we left off in our t-test output. Let's start by verifying our assumptions. We already discussed the independent samples assumption and are content that the height of each student in the class is statistically independent of the other students in the class. Next, let's verify the normality assumption. Ideally, the histograms will be approximately symmetric and have close to a bell shape. While these are not perfectly symmetric, in reality they're probably close enough. Further, when we inspect the QQ plot, we can see that the points pretty closely fall along the straight line representing a perfectly normal distribution. Therefore, we accept that the normality assumptions are sufficiently met. The fourth table in the output formally tests the equality of variances between the two populations. To test the equality of variance, SAS uses the folded F test. The null hypothesis for this test is that the two populations have the same variance. In this case, we say that the probability of getting an F value of 1.25 or higher if the null hypothesis, that the group variances are equal, is true, is 0.5256, or 53%. Therefore, we fail to reject the null hypothesis and conclude that the population variances are equal. In practical terms, if the p-value of the folded F test is less than 0.05, then we conclude that the population variances are different. Okay, now we move up to the third table. This is where we can see the results of our primary hypothesis test of interest, whether mean height differs by gender. And because we just determined that the variances are likely equal, we'll use the p-value derived from the pooled method for our hypothesis test. However, had we found evidence of unequal variance, we could have moved forward with our analysis using the p-value derived from the Satterthwaite method. As you can see, in this case the conclusions we make are identical regardless of which method is used. Okay, now that we've verified our assumptions and identified which p-value to use, we can interpret our results. The probability of getting a t-value this or more extreme if the null hypothesis, that the difference between the sample means is 0, is less than 0.0001. Therefore, we reject the null hypothesis and conclude that the population means are not equal. And again, in practical terms, we conclude that the two population means are different. Before we move on, I want to point out a few things. First, as a practical matter, the number that is almost always used to indicate statistical significance is p less than 0.05. However, there's nothing magic about this number. At some point along the way, it simply became convention. Second, I want to point out that the p-value is not a measure of the strength of the relationship between two groups. Sometimes the word statistically significant can be misinterpreted as scientifically significant. In other words, the p-value, in this case, tells us that there's a very small probability that we would see this big of a difference in mean heights between males and females in our sample if the mean heights in the population are the same. But just because there's a large probability that the mean heights really are different does not necessarily mean that this difference is important or meaningful in any scientific way. Third, even when the p-value is very small, as it is here, there is still a small probability that our conclusions are incorrect. That's one reason why repeated studies are so important. Fourth, p-values are highly sensitive to sample size. So when sample sizes are large, you're more likely to find significant p-values even when the average difference between groups remains constant. And fifth, many people often ignore the assumptions that must be met before conducting hypothesis tests. I'm not saying this is the right thing to do, I'm just saying that you should be aware that it commonly happens. Now you try testing for differences between two means using proc t-test. In this video you reviewed some basic information about statistical hypothesis testing in general. You also learned how to carry out a hypothesis test for a difference between two means.